Hey, this is project number 2 with ECE 4430. In this project, we built some amplifiers with MOSFETs. I'm Joshua Roper.
And this is Xingyan Zhu.
So the first circuit we're going to look at is going to be the source follower circuit. So in this circuit, you can see our settings up at the top, our W over L, our load capacitance, what we want our bias current to be. And so right here you can see our theoretical model of our gain versus VS, our corner frequency, thermal noise, what do we want our linear range to be. So just some takeaways to look at. You can see our gain varies with our source voltage. Basically, as VS goes up, our XD goes down, which makes changes our CD to go up, which makes our kappa go down. So we expect our gain to go down as VS goes up. You can see also in our linear range, we want to eliminate the exponential part, basically. So we want our numerator to be much smaller than our denominator. So those are some takeaways. So for our simulation, you can see in our gain region, we have a slope of 0.8, which agrees closely with our theoretical prediction. You can see we also present our bias current plot, which is roughly 100 picoamps in this region, the linear region. And you can also see our output voltage varies with input voltage. Our kappa basically varies as we expect it to, and it's about 0.8, and it just goes down because of that CD effect we showed. And here's the layout to the right and the schematic. So for transient analysis, we input a step response, and then we look at our absolute value of our output voltage minus the bias point, and then take the log of that. And so we can curve fit this linear region to get our slope, which gives us our corner frequency of 6.55 kilohertz and a tau of 24 microseconds. And also something to note, if you increase above the threshold for the amplifier, basically you'll get the same response at the very bottom, and it will be the same for 0 to 5 or 0 to 10. Basically, it doesn't matter because it's being clipped. And then you can also see we did noise analysis. We integrated over frequency to get our noise plot, and that gave us basically 4 times 10 to the negative 6. You can see our theoretical results agree very closely to our simulated values.
Okay, and for the common source circuit, so basically we follow the same procedure and same setting. So we have our W over L ratio unchanged, and load capacitance also 100 femtofarad, and the biasing current is 100 picoamp. And to get that, we need to set our V bias to be 1.73 volts. And we have several analyses, like our voltage gain, our corner frequency, and our total thermal noise, which is listed here. And to add more, so to increase our gain, we can add more cascode transistor to the NFET and PFET. And the linear range part, we have our differential equation for the capacitor, and we want to eliminate the exponential to linear so that we can keep the linear range. So the linear range should be like this, where the denominator part is lesser than the UT. And for the simulation, we have our schematic and a layout on the right. So from that, we simulate our curve and get the V out over V in. And we can see from the linear range in the middle, which is our gain region, our slope is around negative 184. And to the transient analysis, we have 2 waveforms, one in region and one in the gain region, one out of the gain region, and we flip them and take the natural log and curve fit for the time constant, which we listed here. So the previous part is for in gain region, and the following part is for the out gain region. And here's a table of parameters that we derived.
Next up is the differential pair circuit. So right here you can see our theoretical analysis, which we basically use to calculate V tau so that we can get our I bias to be 1 nanoamps. So in the simulation, you can see in our input sweep, we get a symmetrical response, which we expect, which is slightly skewed due to the early effect. And then when we do a common mode voltage sweep, you can basically see I1 is about half of I bias, which is what we expect since the sum of the I1 and I2 has to be I bias. And you can see our layouts and schematic to the right.
So for the differential amplifier part, we basically built up upon our differential pair circuit and make a 9 transistor one as shown here. And the settings are all the same with previous part. And initially we want our biasing current to be 1 nanoamp, but we found that the PMOS at the current mirror on the top cannot working in the 1 nanoamp based on our model. So we raised that into 12 nanoamp to get the PMOS working. And for the gain, transconductance, output resistance, quarter frequency, we have our formula and calculation result listed here. And for the simulation, we have our layout and schematic on the right. And from that, we simulate our V out versus V in curve. As you can see in the linear region or gain region in the middle, we have our slope like negative 145. And then we do a unity gain setting, and we link the V2 input together. And then we get a unity gain transfer function with slope slightly lesser than 1. And for the transient analysis, basically we follow the same procedure. We have two waveforms, one in gain and one out gain, and then we flip them, take nature log and curve fit to get the time constants. As you can see, the two time constants are really close. So basically there's another way to calculate the circuit parameters. So if we are given a volt source and a ammeter, we can follow the procedures like listed on the left to find the I out versus V out curve, which is the output resistance is just 1 over slope. And following the text on the right side, we can get a curve of the transconductance, and we can get the value of this 2.3 to the 10 to the negative 7th. And then we multiply our transconductance and output resistance to get the gain of like approximately negative 160, which matches with the theoretical result and the transfer curve result. And here is the parameters tables that we calculated.
So for our final design project, we designed an operational transconductance amplifier, or an OTA. So basically, we wanted to get 10,000 gain and bandwidth of 5 kilohertz and with phase margin of over 45 degrees. And so to the left, you can see the schematic which we used to achieve this. You can see we varied some of our W over L's on the cascoded part at the end. We changed our capacitor a bit, and we have our bias voltages for both the cascode and the differential pairs listed to get the bias currents that we wanted to get the gain that we wanted. And so one effect that's interesting to see here is we have a transistor mismatch, which basically you can see the infet region in the bottom of the cascode has 2 current mirrors versus the 1 current mirror at the top for the PMOS. So basically it's going to have a different kind of path, so the currents are going to be drawn slightly asymmetrically. To the right, you can see our layout. You can see on these bigger W over L ratios, the actual region for the silicon region is bigger. So for the DC sweep, you can see we have a 10,000 roughly gain linear slope, which is what we want. And then for the unity gain plot, you can see we have also a roughly 5 kilohertz 3 dB region. And here, this is absolute, so 3 dB translates to 0.7071, or 1 over square root of 2. And then you can also see our phase margin plot, which we have 47 degrees phase margin extra, and then you can see our noise as well.